We have an opportunity now for questions for Ken, Kamalina, and Michael. Questions from the audience. We do have the roving mic working now, so we'll actually be able to hear your questions. Brian, on your left.
So with heterogeneous processing, what's kind of best practices can you suggest for partitioning what parts of your algorithm should go on to a GPU or an FPGA? Or is there any metrics that you guys can use or suggest? What's used out there?
Excellent question. Anyone want to take a crack at it?
I'll have a go. I mean, that's the key question, actually. So I'm not sure if I'm going to give a clear recipe for it. But you know, I think it's quite clear that you know, things like GPUs are very good at applying you know, the same operation to a large number of pixels in parallel very rapidly. So once you know, for example, if you've got a transform, for example, there's a lot of algorithms as are kind of adaptive. So you know, you're doing something to your pixels which is based on some input. So once that transform has been generated and you want to apply it to some pixels, maybe it's some kind of normalization. So you could think of it like if you had a Gaussian blur, but that Gaussian shape is dependent on some other input. Once that transform is constructed, you can probably apply it very rapidly to your whole data set using the GPU, the shaders. But constructing that, the kind of higher level processing, which is not pixel intensive, but might be intensive in other senses, naturally fits much better on a CPU. So you find a lot of algorithms where there's a non-pixel, a non-per pixel operation, but quite complex maths done on the CPU, and then once the transform's generated, you can map it to the GPU. That's one way of partitioning.
Yeah, I think that's a good way of looking at it. And also you have to consider the problem globally, because if you just take your whole algorithm chain and you say, well, this block's better here, and that block's better there, and this block's better there, you may wind up with an absurd amount of data movement back and forth. So often what happens is the block in the middle winds up going someplace where it's not really optimally suited, but it doesn't make sense to ship, you know, vast amounts of data off to something else for a microsecond just to get it then have to move it back, essentially Amdahl's law. So that's the other piece. I would say, you know, you got to look at the computation rates, the style of computation, what kinds of parallelism are available in the algorithm versus supported in the processor, and then also sort of optimizing the data flows. Other questions from the audience?
A follow-on question to Michael's argument, do you see a standard architecture for a vision processor emerging? Because say you could lump the CPU, the GPU, and some FPGA elements onto one die. Is there enough structure and repeatability in the algorithm, say for the camera example you had, that we could go and all share one processor?
Yeah, I think from our perspective, what I think is going to happen is that, quote unquote, what you say describe as a VPU, I think is going to sit between the camera and the rest of the system. So you will do a lot of the pre-processing up front, and then should spit out just the process data so that the rest of the system can digest more easily. So I'm not sure, it's going to get all merged in anytime soon. That you're going to have this one function that is going to do a lot of that vision processing separately. At least that's my opinion.
I think the applications are just too diverse. And there are also kind of not strictly technical reasons, back to the previous question, why certain blocks wind up implemented on certain kinds of processors. To Ken's earlier comment, sometimes you just can't find a skilled programmer. It should be on the GPU, but you don't happen to have a GPU guy around. And the guy that you do have, you can't afford the extra 90 days it's going to take him to get up to speed. So oftentimes it's those not strictly technical considerations like what development skills do I have available today, and also kind of risk management about who's my supplier and how confident do I feel about committing to this supplier that come into play beyond the purely technical analysis of what data types, what style of computation, and so on. But bottom line, I think there's just too many factors and too much of a diversity of applications for it to converge to one style of processor.
I might add just one thing. I think compilers are very important. I mean, if you look at a mobile application processor, you've got multiple CPU cores, multiple GPU cores, at least 2 SIMD cores, and some other things as well. How do you program them? How do you distribute your code? How do you schedule it? How do you avoid things waiting? How do you share memory? I think compilers need to be developed to handle these heterogeneous systems.
Yeah.
Yeah, that's a good point because, I mean, we did like one project, it's not quite the compiler issue, but especially with the vision processing, it's so algorithmic, and then we developed this one application. We thought we're kind of done. Okay, let's multi-thread it, and we start multi-threading everything, and then we start using it in the field and say, okay, that doesn't work. We got to reshuffle everything, and now it doesn't work multi-thread anymore. We got to re-multi-thread everything all over again. And I was like, wow, this is a real pain in the butt. Yeah. So.
We hear that a lot. Yes, sir.
Compiler technology isn't something that I follow, but from dissertations that friends of mine were doing 15 years ago, it seems like the basic infrastructure for the kinds of software tooling and compiler tooling that you're talking about exists. So I guess it seems more like not the lack of a technology problem, but a technology transfer problem. So I guess my question is, what would you accept as a product from the compiler community that would be something that you could both understand and use in the available time to solve this problem? Because I think the compiler tools are there. They just need to be adapted to the kinds of resources that you're talking about.
I think, from my point of view, I would say that what we see is that, for example, C or C++ isn't often a very good place to start for parallelization, because compilers which will take each line of code or look for parallelization within serial code, we've never got great results with those. It seems to be almost something you have to go to a very high level, something like MATLAB, and look at because I think languages like that are quite parallel in their construction. So I think I think our feeling is that probably compilers that can go from a very high level language are probably more appropriate, I think, for what we're looking for.
If you saw that kind of compiler, then you would consider buying it and using it.
Yeah, if it worked, absolutely. Yeah, so save us a huge amount of time.
Yeah, part of the challenge, though, is when those things emerge, they're often coupled to a specific architecture from a specific silicon vendor, which may not be the specific silicon vendor that's ideal for your application, or even if it is, you may be hesitant to buy into a design flow that then locks you into that silicon vendor and only that silicon vendor. So I think that's one of the challenges with compiler innovation is, it's going to start on one architecture from one vendor, and it's going to take a bit of a leap of faith for the early adopters until it's broadly available. But until enough people take that leap of faith, it's not going to become broadly available. So a bit of a chicken and egg problem, I think. Yes?
Yeah, I'm surprised nobody has mentioned DSPs as another option of doing a heterogeneous embedded vision implementation. Do you have experience on DSPs, and can you elaborate on pros and cons?
Well, in response to that question, I have to applaud the presenter from Texas Instruments, Goxel, for maybe not even mentioning the word DSP in his presentation, but his presentation actually was about implementing vision on the DSP, and he showed performance data for the moving object segmentation algorithm implemented on the DSP with various resolutions and frame rates, and he has a demo in room 101 of the same. DSPs have often been the default processor choice, in fact, for vision algorithm implementation because they're, in some sense, what people think of first for embedded processing applications that are of a data flow and highly parallel and signal processing nature, which many of the vision algorithms and applications are. And so you do find them used in plenty of products today. The difficulty that we sometimes find is that even though DSPs are more powerful and more efficient than a CPU, comparable CPU for these kinds of algorithms, they often aren't powerful enough, especially when you get into high definition, high frame rate video. And so the DSP then needs additional help. And hence, in the analog devices presentation earlier, you heard a little bit about, okay, analog devices has the Blackfin core, which is a hybrid CPU DSP. They put 2 of those on the chip, and then they bolster it with a specialized parallel processing engine to offload some of the most processing intensive portions of the vision algorithms. Any other comments on DSPs?
Well, actually, I don't know what happened to DSP. I used to use DSPs a lot, and it was so big, 20, 30 years ago. I mean, everyone wanted to learn DSP. But I think it's more marketing issue. I don't know exactly what happened there, but if you look at a lot of the mobile platform now, there's no DSP core. But you do find CPU and GPU, so.
Well, it's interesting you make that comment, Ken. Actually, the mobile application processors usually do have a DSP core, but it's typically hidden. And it goes to Michael's point about the mobile application processor, like you find in every smartphone from Qualcomm, TI, whatever. They have this plethora of very powerful parallel processing engines, but you're not allowed to program any of them. You're typically only allowed to program, as a typical user application developer, you're only allowed to program the CPU. You can't get access to the 90% of the processing power that's in the ISP, the VPU, the DSP, and so on. So it's interesting that your impression is that they're not there. It's true in some application processors, but most of them actually do have it. You just can't get to it. It's hidden.
Okay.
Any other questions? Sir, here in the front.
The most powerful machine that I know that recognizes images is that, I'm sorry, the most powerful thing that recognizes images is our human brain. So we figure out distance, we figure out many things instantaneously. Did you ever take in consideration how the human brain can do this? And
Well, see, the problem is that the human brain is associated also with a nose, so it just won't work in the hog barn.
Yeah, I mean, I'm not sure. I think one of the speakers mentioned earlier, you're not necessarily trying to replicate human, but there's computer vision can do things that human brains cannot do. I guess and one of them is like measurement. You can make very accurate measurements using a 3D camera. The human brain cannot tell a difference between a hog that weighs 140 pounds versus 145 pounds. Okay, human, it just can't. It's not possible. So I think those are where you can really add a lot of value.
More directly to the question, there are at least a few companies and researchers working on vision algorithms and architectures that are inspired by the human vision system. One company I know of is called Euticus, EUTECUS, I believe. It's a US-Hungarian company, and they actually implement vision applications on FPGAs, but they implement an architecture on the FPGA that is in some sense inspired by the architecture of the human vision system. So they're trying to take their inspiration from the human visual system. But I think that approach is more the exception than the rule today, at least in commercial applications.
And I guess building on that, there are some, the human brain is very qualitative in how it analyzes things compared to some of the, computation or algorithms that we implement in computers. So there are application areas where there's a lot of research and implementations that have been done to do qualitative analysis of video streams, for example. Another implementation that is maybe similar to human brain, or at least human functionality, is stereo vision in a way, because it relates to using 2 different sensors and putting the image data together to form an image.
and another interesting point is it turns out science doesn't actually really yet know, in many cases, how the human brain works when we make certain kinds of decisions. There's a fascinating book called Incognito by a neuroscientist named David Eagleman, which I highly recommend. And one aspect of that book is about how we take in information and make decisions, and how we actually just don't know in many cases. So if we don't know how it works, of course, then it's hard to emulate it.
you don't analyze pixels, right?
Right. For sure, we're not analyzing pixels. Any last question for this fantastic group of speakers?
Do you have any comments on how time-of-flight cameras or other specialized cameras that give 3D information will affect embedded vision? Will it offload some of the processing so that more capabilities are out there, or what impact will it have?
Well, you're probably in a better position.
I mean, we don't, I like to go back to the Kinect issue, which is just, Kinect's just been amazing, revolutionary in terms of the not just the technology, but more so on the market side. And there's a lot of other time-of-flight cameras that's coming out that's really good, low cost, low profile. So I think we're just kind of beginning of this whole revolution of these new type of camera that they can be used in all kinds of different applications. So I don't think there's any one particular type of camera that's going to dominate. I think there's going to be so many because there's so many different applications that require different. It needs to work in different environments, different cost factors, and so on. So yeah, I think generally it's good.
And in addition to the hardware, there's also a software aspect to it. In the past, sometimes 3D systems were very complicated to program, but there's been an emergence of a lot of different 3D programming tools out there to make that bar lower and to make it easier to begin programming a 3D vision system. So I think that in combination with the cost of the sensors is going to be important in that affecting embedded vision.
Later today, Eric Grigori will be doing a presentation on sensors, and he'll talk about some of the categories of 3D sensors. What I find very interesting is when you think about the trade-off between 2D and 3D, in some cases, going from a 2D sensor to 3D sensor actually drastically simplifies the processing. Because, for example, if what you're trying to do is separate foreground from background, that's just dramatically easier. It becomes a simple thresholding operation with 3D data, whereas with 2D, you have to go through all this complicated heuristic guesswork to decide what's foreground and what's background. On the other hand, with 3D sensor, especially if you're using it in combination with the 2D sensor, as is usually the case, you get massively more data now that you have to process. So depending on what you're trying to do, it may actually result in higher processing requirements and more complex algorithms, or lower processing requirements and less complex algorithms when you switch from a 2D to a 3D sensor. Great. Well, I really want to thank our excellent presenters in this session. Thank you very much, Ken, Kamalina, and Michael.